Welcome to today's explainer. Okay, let's dive right into this. Today, we are cracking the absolute ultimate puzzle of atomic stability, Bohr's theory of electron orbits. Have you ever stopped to wonder why everything around us, the screen you're looking at, the chair you're sitting on, literally your own body, doesn't just completely fall apart into nothingness? Well, it all comes down to a tiny subatomic mystery that completely baffled the greatest minds of the early 20th century. It honestly sounds like science fiction, but the very stability of our physical world hinges on this microscopic balancing act. Think about this for a second. If an electron is constantly moving in a tight circular path around a nucleus, classical physics dictates it absolutely must be gaining acceleration. And while any charged object gaining acceleration is bound to liberate energy, right? So, logically speaking, shouldn't that electron continuously radiate energy, lose its momentum, and just spiral right down, eventually crashing into the nucleus? It's a pretty terrifying thought experiment that questions the very fabric of reality. Because if classical physics strictly applies at the subatomic level, atoms should literally destroy themselves. And that brings us to Section 1, the collapsing atom paradox. Ernest Rutherford had a really commendable atomic model that correctly identified the dense nucleus at the center. But it had one massive theoretical oversight, an oversight that threatened to unravel our entire understanding of physics. Let's walk through it. Step 1. Imagine the electron moving at breakneck speed in a circular path. Step 2. Because it's constantly changing direction in that circle, it's gaining acceleration. The problem? Classical physics dictates that a charged particle gaining acceleration must liberate energy. So step 3, if it continuously keeps radiating this energy as it circles, its orbit would inevitably shrink. Ultimately, all the energy would get depleted, and boom, it crashes straight into the nucleus. The mathematical result of this sequence is the complete and utter destruction of the atom. Now, what's really interesting about this is the massive contrast between our theoretical math and what we actually see out the window. On the theoretical side, we'd expect high instability and total atomic collapse. But on the side of natural reality, look at a simple tree outside. All the atoms in that tree, and everywhere else for that matter, are completely beautifully stable. If Rutherford's classical physics application was 100% correct, that tree and matter itself simply wouldn't exist. So, was Rutherford entirely wrong? Actually, scratch that. He wasn't entirely incorrect. He just needed a brilliant modification. Which brings us to Section 2, Bohr's brilliant modification. Enter Niels Bohr, the legendary scientist who provided the crucial plot twist that essentially saved the atom from destroying itself. Bohr introduced a real game-changer of a concept known as discrete orbits. He stated that there are certain special allowed paths inside the atom. An electron can't just be floating around anywhere it wants. It has to be locked into one of these specific discrete orbits. And here is the absolute magic part. When an electron revolves in one of these special orbits, it does not radiate energy. So the crucial point is laid out right here in Bohr's postulates. Rule 1, only certain special orbits, these discrete orbits, are allowed inside the atom. Rule 2, while revolving in these discrete orbits, the electrons do not radiate energy. This simple rulebook completely overrides that classical physics paradox we just talked about. Bohr essentially broke the known rules of classical physics to make this work, which is an incredibly bold move, but it definitively tells us why an atom is so stable. You might be wondering, though, what exactly do these discrete paths look like? Let's visualize this in Section 3, the atomic solar system. Sometimes, to wrap our heads around the unbelievably small, we kind of have to look at the incredibly massive. Picture our own solar system. We know the sun sits stationary at the center while the planets revolve around it in fixed paths. You never find a planet randomly jumping to a completely different path out of nowhere, right? They always encircle the sun in their defined lanes. Well, in a remarkably similar way, we have the atomic structure. The dense nucleus acts exactly like the sun, anchored at the center. And the electrons? They're basically our planets, revolving around the nucleus in fixed, defined orbitals. That naturally leads us to Section 4, mapping the energy levels. Now that we know these fixed electron orbitals exist, how do physicists actually identify and name them? Because they're frequently referred to as shells. Remember how Bohr suggested that these revolving electrons don't radiate energy? That makes perfect sense when we use the specific term, energy levels. This means that each shell has a strictly defined energy level. Because electrons are securely locked into the specific energy state while inside their shell, they simply do not liberate any form of energy while revolving. This bold concept is literally the foundation of atomic stability. And this brilliantly illustrates exactly how we mapped them out. Starting from the orbit closest to the nucleus, we can name them alphabetically, starting with the K shell, then the L shell, the M shell, the N shell, and so on. Or, if we want to number them mathematically, we use the lowercase letter n. The shell closest to the nucleus is n equals 1, the second is n equals 2, the third is n equals 3, heading outward. Whether you use letters or numbers, this framework firmly establishes an electron's exact position around the nucleus. Okay, moving to section 5, the final subatomic particle. So we've got positive protons in the center and negative electrons locked into their energy shells. But we aren't quite finished yet. The true story of the atom goes a bit deeper. I want you to ask yourself, with positive protons heavily packed in the nucleus and negative electrons revolving in fixed orbitals, is that the complete structure of an atom? Or is there one more subatomic particle left hiding in the center? For years, science actually thought the picture was complete, but there was a mysterious missing piece when it came to the overall mass of the atom. It just didn't add up. Let's move to 1932 and see how this builds. Prior to 1932, the consensus was that the nucleus contained only positive protons. But in that year, a famous English physicist named Sir James Chadwick made a monumental breakthrough. He discovered the third subatomic particle, which rapidly established the complete modern design of the atom we use today. Chadwick's newly discovered particle was absolutely fascinating. First, he found that it perfectly balanced the scales. It had a mass almost exactly equivalent to that of a proton. But what about its electrical charge? Astonishingly, no charge at all. It was completely neutral. Because of this, it was named the neutron, denoted by the lowercase letter n. It perfectly rounded out the heavy center of the atom without adding any crazy repelling electrical charges into the mix. So, by putting together the discoveries of Rutherford, Bohr, and Chadwick, we finally arrive at this elegant summary: the complete design of an atom, a central, dense nucleus packed with positively charged protons and neutral neutrons, all smoothly surrounded by negatively charged electrons revolving cleanly in their fixed, discrete orbitals. It is an incredibly balanced, stable, and quite frankly, beautiful system. But our journey into the atomic world doesn't fully end there. A final, really compelling mystery remains. How exactly are those electrons distributed in their respective orbitals? Like, are they just randomly scattered? And what is the absolute maximum number of electrons that one specific orbital can hold? There's a strict, undeniable rulebook for this too, and it dictates how every single element in the universe interacts. It's a massive puzzle that I want you to think about. Keep questioning, keep learning, and thank you so much for joining me for this explainer.